So this is a problem we worked on from class, and we solved it with change in momentum. Now, another way to solve it, we said you can either do change in momentum, force times time, or you can do it as conservation of momentum. So that equation was momentum total initial or equals momentum total final. So the initial is before the collision, or in this case, the explosion. So up here, this is beforehand. Right? We saw before you shot the gun, the velocity was 0, so this entire side is 0. Afterwards, momentum total final. Well, I can see that the bullet is going forward, so it has to have momentum, and I should know that the gun has to go backwards. Now the reason, why does it have to be momentum? Well, I would have momentum of the bullet. Right? Now this has to equal 0. So if I have positive momentum from the bullet, because it's going to the right, I will have to have a negative momentum of this bullet because it's going to go to the left. So this is momentum of the gun plus momentum of the bullet. If I end up looking at this problem, I could then say, well, negative momentum of the gun, I moved it over by subtracting it, equals momentum of the bullet. Right? And this is the exact same thing we had in the other problem, because you can see here was the momentum final of the bullet equals, and over here this was the final momentum of the bullet or gun. Right? So here, plugging these numbers in, I have this equals mass of, well, just this term equals mass of bullet, velocity of the bullet. So we did that before. That was right here. And so this ends up with mass times velocity of the bullet, and that is 35.7 kilograms times meters per second equals momentum of the gun, but negative. So then I need to find velocity of the gun, so this would equal mass of gun, velocity of gun. Right? Sorry about that, that's a G. So then I can see here I end up with plugging in the mass of the gun, so this is negative, well, I'll just look here, negative 5 kilograms, because that is the mass of our gun, equals 35.7 in the VG. So just do the same math as we did before. So that's one other way to solve the problem. Now what I want you to do is go down to the bottom of this page, and let's just make another problem. So in this video we're going to watch two teachers running towards each other in giant inflatable spheres. So let's see what happens. So here's the teachers, they're running towards each other. And they have momentums and then they go away. So not all problems always stick together. This is one where they did not stick together. Now, let's go and talk about the physics that happened here. Right? So, Mr. LaCour, you can see he lost his glasses because his glasses were in motion. Nothing acted on them, so they kept going. Mr. Hare, same thing happened with his contact. Now here, I'll model out the collision. So I had Mr. or Montrell, right? He was running in his bubble with this velocity. Okay, so this is initial and final will be down here after the collision. Here I had Mr. Hare, or Tyler, right? And he was moving this direction. After the scenario, we could see Mr. LaCour ended up going back this way, and Mr. Hare, or we were calling him Tyler, okay, goes back this way. Okay? So now we can also look at it here. We can look at, we know this problem, I like to analyze it this way. Change in momentum of Mr. LaCour equals the change in momentum of Tyler. Right? We can see that Mr. LaCour had a positive velocity, then he ended up with a negative velocity. So he had a positive momentum, and now he has a negative momentum. So he lost momentum. So I could say that's a negative because his momentum changed in the negative direction. Mr. Hare started off with a negative velocity and ended up with a positive velocity. Right? So he gained momentum, so that's why we see this as a positive. Right? So I'd have to know, how much Mr. LaCour gained or lost, but I'd have to have those velocities to figure that out. But this is another way we could have written this problem. Now either I can do it step by step, and I could end up with this other equation, which was before the collision. I notice I have two objects, right? So I have to add up our total momentum before. This is mass of Montreal times velocity of Montreal plus mass of Tyler. That's a plus sign. Velocity of Tyler. Now this also then that's initial. So that was to the left side, or the top side there. This then equals, here's Montreal. He has a momentum afterwards. So he has mass of Montreal, velocity final of Montreal. Plus, got to add the last piece here. Afterwards, I can see that Tyler has a velocity, so he has momentum. So mass of Tyler times velocity final of Tyler. And that's all I have to have. So in this one, I can see in my equation I have two objects before that had momentum. So I have two objects before. Has to equal the total momentum afterwards, which is over here. I can see I have two objects, and I have two objects. Right? So you can always look at your picture and see the total objects that you have, and the total initial objects that you have on both sides, and your equation should add up to those variables. Now, you'd still get the exact way solving this. We'll look at some more. A lot of times it may be easier to solve it this way, or other times it's easier to do the momentum total initial equals momentum total final. It just depends. You'll have to experiment which is going to be easier on which problems.